Welcome to my presentation. My name is Job de Haas. I'm one of the directors of a company called Riskcure. We're based in the Netherlands and we focus on hardware security testing. So maybe some of you have seen the talk this morning by Chris Tarnowski. That's an area where we are active, although not in the detail that he does. Our main focus is side channel analysis. We've been doing that on hardware like smart cards for a long time. Since 2 years, we're also expanding into embedded systems. And today I want to discuss with you what the impact of side channel analysis on embedded systems may be in the future, and maybe in the near future. One other issue I had is that I crammed way too much into my presentation, and I have less time than I did the talk last time, and I also don't have an assistant that I have had last time, so it will be very tricky to get everything done. Also, I have the problem that my PC wasn't working with the screen, so now I have to switch to here, and hopefully it works. Okay, can everyone hear me fine? Okay, then that's at least not an issue. So what I want to discuss with you is three aspects. First, I want to show you a little bit into the embedded, or introduce you in the embedded area security-wise, what's happening and where it's moving to. And you'll see quite a bit of similarities with the talk of this morning by Chris with what happens in the chip and what's actually happening inside an embedded systems today. The second step I want to do is introduce you, give you kind of a background primer into side channel analysis. Who here has knowledge of how you break a key using side channel analysis? Okay, so it's actually going to need a real primer in that sense. Because then, after that, I want to explain actually how you're using it and how you can develop countermeasures against it. Because again, in the hardware world, smart cards, there have been quite a development over the past few years in implementing countermeasures against these attacks in hardware. However, an embedded developer generally doesn't have that much control over its hardware. You have to buy off the shelf. But luckily, there are still some things that you can do in software to at least reduce the leakage, if not fully prevent it. So, in the third part, I hope to show you some examples of that. First, so I keep on using the wrong keyboard now. What kinds of embedded systems with security do we see? Well, the first thing that also was mentioned this morning is the USB sticks with fingerprint recognition with crypto inside. We see mobile phones with NFC, that's proximity payments. You just wave your phone in front of the terminal and you pay, which of course will also require a significant amount of security inside that phone. Set-top boxes, high definition content, prime movies that will be stored and transmitted and received by those boxes using a lot of crypto. And finally, game consoles, actually an area that has moved quite a bit over the last few years with the Xbox 360 as one of the best examples of high security devices, using a lot of hardware, low-level security to protect the system. So what are they protecting against? The thing you see mostly in embedded systems is in three areas. And actually, when you look at them, they're actually pretty obvious and pretty simple. And actually, this is still an area where there's a lot of improvement to be made in embedded systems. First thing is removing debug access. When you develop an embedded system, it's much more difficult than an open platform like a workstation running Windows or whatever. You don't have that much access, so you want to have these extra interfaces to help you develop. But you don't want to have these interfaces in your production system because they help the attacker pretty much do what the developer did already. And they're very convenient in that sense. So removing them or making them only accessible after password checks or secure authentication is something you see now in new embedded systems. The other one, again, from this morning, very great analogy is the use of buses. On your PCB, you have buses running even more open and wider than on a chip itself, which also transmit code going from the flash memory to the CPU to the RAM area. These need protection. The chips themselves need protection. And you see these features slowly entering also in embedded systems now. And then the last part is actually also quite significant. Protecting the integrity of the code that's allowed to run on the system. So it actually prevents you from writing your own application and running it on the system. And this goes from simple boot checks, where during booting a hash is checked, a signature with public key system is checked, to full runtime integrity checking that can run in sometimes sub-second over the whole memory space, doing SHA-1 hashing, for instance, making it quite difficult to inject changes into your code. All these measures have some basic objectives. So the first one is prevent running the unauthorized code, because that allows you basically to change the function of the device, take away any access controls that are implemented in the software, and also maybe a stepping stone towards more internal secrets in the CPU or in the system. And that's actually the second step, so protect that confidential information, the secret keys that are in the system, while the system actually is out there in the field. So it's not something you really tightly control. What you see with these measures is that it actually prevents the device up to a certain level against pretty conventional attacks, as I call them, which are attacks that you can do at home, attacks that you can scale up, like a repeat attack, where you can explain a user, open your box, these are the screws that you need to remove, you need to connect a wire here, you need to connect my device that you can buy from me, and then it's broken. So these kinds of attacks become harder because you need to physically open your device much deeper by opening up the PCB itself, or taking away hard epoxies or things like this. They don't really prevent the hardcore deep first time attack where you spend a lot of time. That's something these attacks generally won't prevent. So with this higher security level, I think I have a picture, but that pretty much says everything I just said. So you see the attacker moving because it becomes more difficult, and then the protection moves and becomes more difficult. What you generally see is that the movement is a little bit in the same direction as smart cards have gone. So smart cards started as these very simple 8-bit CPUs that were basically wide open physically. They were very well protected maybe from a software point of view, but even then, not always. But they start to become much more these fortresses, protected units, and that's also something you see happening in the embedded world, where the CPU is actually taking this role. Now, in the smart card world, we have seen side channel analysis attacks for about 10 years now, and what we see is that there's a lot of countermeasures being implemented at that level on smart cards. We don't see them at all in embedded systems. So that's one of the reasons we think that these kinds of attacks will become one of the alternatives for an attacker once a lot of those non-invasive attacks start failing. Okay, so that's a bit of the start into embedded system security. Next thing about side channels. So what I want to show you is a little bit what are side channels, what can you do with them, and how do you use them during an attack. So first of all, what's a side channel? Well, basically a channel is a means of communication. It's a channel that conveys information about something. And logically, your channels are your keyboard to enter information, your screen to receive information, a serial port. A side channel is a channel that does the same thing, but is not meant for that purpose. So, and the side effect is that, for instance, by looking at the power consumption, you can see something about what the CPU is doing. And it's giving you information about what it's doing through a channel, the power consumption, that's not intended for the purpose, and generally even not known to exist to a normal developer. And what kind of channels do you have? Well, one of the best known, I guess, is timing. Timing attacks are, well, the group of side channel attacks that you also now see in the kind of normal PC world. We've seen attacks on OpenSSL implementations, even from remote over the network, by just looking at the timing differences certain crypto operations take. Because, for instance, the code path is different for certain key material or data material. The Xbox 360 recently was broken. At least the break was in a certain version, but then they upgraded the version by Microsoft to a version that you could not roll back. And now they broke the downgrading by doing a timing attack on the HMAC, the message authentication code, which is a code that's compared byte by byte, but the compare function quits after the first non-equal byte. So by looking at the timing, you'll see differences if 3 bytes are equal and then there's a mistake, or if 5 bytes are equal. It takes a little bit longer for the compare function to terminate, and from that timing difference, you can have kind of a brute force attack on each byte, only 256 checks, and then you'll see a timing difference for 1 byte. You know that's the correct one, and so you walk the whole 8 bytes or 16, whatever the length. Power consumption, electromagnetic radiation, we'll show you a little bit later. Light emission even can be a side channel. For instance, even modem lights. They can be very tiny, but they reflect against a lot of surfaces, and by looking from a distance with a telescope, you could even figure out what the LED is doing, and if there's a correlation with real data, that will actually transmit the data. Sound, keyboard typing is a known side channel. By monitoring the typing sound, you can figure out what someone is typing with a combination of statistical analysis and maybe stereo reception. So there are quite a few side channels. So what do you do with them? We distinguish basically 2 types of uses. The first one is passive, and passive is really you measure the signal and then you analyze, but you don't really influence the system. And the other one is active. This morning also there was talk about voltage glitches, optical glitches, the way where you start operating the system outside of its boundaries. Maybe lowering voltages, toying with the clock will induce faults. And it might be simple faults like, okay, this is a decision point and I want to throw the switch to a different decision. But it may also be in crypto operations. And you can show that in a lot of crypto operations, if you have it running with the correct key and then induce a fault, from the differences in the crypto results with the same input, you can deduce information about the internal key. So there are a lot of attacks possible with these fault injections, and it's a very powerful technique. But we'll focus on the passive attacks for today, and look at what you can do when you look at power or electromagnetic field. Well, this is a short example. I just explained the timing. If you have 2 timings for one process or the other, if you just look at the timing, you can know what the decision was. If the decision depended on a key bit, you'll know that bit for the key. Power. Circuits consist of transistors, of gates. They switch, and when they switch, they consume power. So transitions from 1 to 0 and 0 to 1 are the ones that are actually consuming power. And on every clock cycle, this will happen. So what you'll measure at a certain clock cycle is an aggregate of all the switches happening for that state. And of course, a lot of things are going on, but if at least some of those switches are depending on, for instance, the key, if it's doing some part of the crypto operation that uses that key. So you'll find that there's a correlation between the power consumption at a certain moment in time, depending on the switches, and the switches depending on what actually the key was. And that's what we're searching for. Is this still clear for everyone? Because I'm rambling on. And, okay. The reason I'm a bit rushed is because I have no idea how I'm going to end up in the time. So that's the main reason. So power is quite well known as a side channel. What we've been doing, and that's not something we invented, but the general knowledge is that if power runs through a wire, you'll get an electromagnetic field around it that you can measure, and that will be related to the power that's flowing through that wire. Now, why would you start using something like this if you've got the wire and you know the power that's going through? Well, if you look at a smart card, the power line going into the system is quite of a one-dimensional thing. You can't, the manufacturer can put all kinds of equipment like noise generators and voltage flattening behind that line in the chip, and you cannot look beyond. So you can only hope that it's not perfect and it will leak out a little bit of information. But it can block your view on what is actually happening inside, because the power signal will be very, very noisy. However, the electromagnetic field is something that will be present all over the surface of the chip. It will not only, be the line that's going in. It will be something that's a combination of all the small lines of signal that's on the chip that will create this field. And if there's only one bit that's interesting, it will have a little bit of influence in that field. Of course, there will be a lot of noise, but there will be a little bit of influence. And if you do sufficient statistical, like big population of measurements, you will be able to find that signal in the noise. So actually what you see there is a probe in a kind of an XY station. The probe is actually here on the table also. So it's something that we designed and we use that for our own analysis. And I am going to show you later what kind of signal you get out of that if you put that above the chip. So what do you do? What you do is you use probes, you use digital measuring equipment, like a digital storage scope. In this case, I have quite a cheap USB scope going to about 200 megasamples. In the office, we use things that go up to something like a gigasample, 10 gigasample. And that is used to capture the signal. Of course, with CPUs running at high speed, you want to have high bandwidth because that's, in principle, everything is happening on the clock. So if the clock is running fast and you want to look in the clock cycle period itself, you have to sample much faster even than the clock frequency of the device. That doesn't have to say that you cannot do anything if you can't do that. Because sometimes, due to the process being much slower, for instance, the software implementation of an RSA, that's much slower than the clock speed itself, you can sample at a much lower frequency and still get enough information from it to look at key material. In the end, what you use is a computer with analysis software to do your statistical and signal conditioning, so digital signal processing, to condition the signal to do your analysis. So this is the next step in what we're doing. So what we do now is we mounted the EM probe in an XY station. So we scan the surface of a chip. And that allows us to create an image, and I'll show you later, of the spectrum above the chip. And because in the end, what you add to the power measurement is one-dimensional. You just get a signal in time. However, with the EM, you have to move it or position it above the chip. So what's the best position? What's the position that actually measures the operation where the key material is happening, and that you're not looking at something like the serial I/O or the external DRAM bus, if that's not an interesting area. So we use this equipment to help us search for that best location. So what I've here is something I just got off eBay because it's nice and cheap and still contains a full Linux embedded ARM CPU. It's an OMAP chip. It's like one of the oldest TI OMAP chips that is now the big line of phone chips. So probably if you've got Nokia phones, and a lot of brands of phones run on the OMAP chip these days. But it's a very, very old generation. It doesn't even have hardware crypto. So everything I'm showing is a software implementation of crypto to make it more visible, because else we'll be looking at really just 2 samples or 3 samples, and now you can really visibly see the signal of a crypto operation. Right, so what I've got here is a probe that you see there. I think there was a pointer somewhere. So this is the probe. It's one package, and it contains the amplifier and a sensor, which is basically a coil. To pick up whatever happens in here, then it goes into the scope. We also supply a trigger signal to know when the crypto operation is happening. Of course, if you're attacking a system, you may not have that easy access to a trigger signal, and you have to find it somewhere else in the signal to find a pattern or something to trigger on. And then we store the results in the PC to analyze. So now the problem is that I didn't get the monitor to work, so I have to switch over, and I hope that this somehow keeps working. This doesn't look good. Ah. Okay, so what I can do here is, it doesn't really fit. Let me resize a bit. So, this is the analysis software that we use for this kind of work. So what I can do now is I can just run a few measurements. The acquisition. Hope it still recognizes everything.
So that's the raw sample at the top?
Yeah, this is a measurement, but now I'm going to do it again to show you that it's actually coming off the device, and then I can also show you. Scope is not available. This is the drawback of cheap equipment. So what I'll show you is that when I do the measurement, first of all, well, maybe it's a bit difficult to see this way, but if it runs, you'll see it better. So the question first is, of course, what kind of crypto is happening here? Now I hope it loads. Yeah. So I think I can just go. Okay. So if I start moving the probe now, you'll see things happening. So here there's more signal. And what actually is happening here, let me search for the best spot. It's not very easy to see. Oh, now the trigger is missing. So what you see is actually it's continuously triggering the same crypto operation. And what's here to start is starting here again. So this is just a repetition of the first part. And if you look very carefully, you see these small humps. And actually, if you count them, there are 16 of them. So anyone know what crypto does 16 times something? Yes. So this is a DES operation. If you would see 10, it is more typical for AES, for instance. So you can already see that there is the pattern of the DES operation is visible even to the naked eye. It's not even drowned in noise, although it's a bit noisy a signal. You can imagine that if you see something like this, that there must be somehow a relationship between what's going in data, what the key is, and what kind of processing it's doing. Because if there's like a 0, 0 on the bus, and then you do a move to FF, there are 8-bit switching. But if you load a 1, there's only 1-bit switching, so there's a different power consumption. Okay, so that was just a short demo. I think, wait a minute. Yep. Now, the other thing that we can do with this, and I told you about the XY plot. So here I prepared a plot. I hope still there. Yeah. So what we can do there is we can scan over the surface of the chip, and then for each position you do a measurement like this. So you trigger a DES and you do a measurement, and then you start to look at the spectrum. So you do FFT of it and look at the frequency spectrum. And what this does is plot over the XY the intensity of the spectrum. And we can chop that spectrum into pieces. So this was the whole spectrum from, let's say this was 500 megahertz. So from 0 to 500 megahertz, it looks at the intensity of the whole signal. So that's basically the amplitude in this case. But then we can chop it up. So let's say in 256 bits. And then I can start stepping through the spectrum. So now you see this is from 0 to, well, what is it? 1.9 megahertz. So it looks a bit noisy. But here you see some patterns. And so for each frequency, there's a different area active on the chip. Actually, this is all a bit on the same side. I'm trying to see what the reason is. Okay, yeah, so here you see that for some frequency, there is an area on this side of the chip. And, well, to figure out what this means, you actually need the pictures that Kristanovsky was showing this morning. You need a mapping of the physical chip compared to the signal picture, and then start to analyze if what's coming off like the crypto core on the chip correlates to some signal in the spectrum that is stronger, for instance, and that may be a free running clock of the crypto part that allows you to zoom in to the correct place. Okay, so then we switch back again. At least I hope. Okay, so that was actually this explanation. So just move over. But like I said, you can do more. What we saw was looking at it like this. So again, you see a measurement of a DES. And that means that actually what you're already doing is reverse engineering, because you're looking inside the device and you may not even have an idea of what crypto it's using, but now you know it's DES. So you can use this to do reverse engineering of the device. What we call this is SPA, or simple power analysis, because you're only using one trace, or you're using an average of a number of identical traces, and only look at the features that you can visually see. In the bottom trace, you see two traces that are, at the start they are identical, but then they start shifting. In this case, we know that this is due to an implementation fault. What's happening here is that there is a table of 512 indices, bits, and it's an 8-bit processor. So it has to do a lookup in this table, and depending if you're in the lower half or the upper half, it has to do a jump, it has to do a test, and then it takes a little bit longer for one half of the table or the other half of the table. Now in itself it's not a problem, but it becomes a problem when this choice is related or directly caused by a key bit. Because now you can see, oh, it's a short one, so the bit is 0, or it's a long one, the bit is 1. And you just need to do the number of key bit tests for this implementation. And actually this is from a GSM chip. So this is, I think, Comp 128. Where actually in the C code you wouldn't see anything, because the people that were coding the C were just creating a table, a char, unsigned char, you know, a 512 index. But the compiler will make this choice for you. So you actually don't even see it when doing a source code review in C. But actually that was not even the most powerful type of analysis, because often you have a lot of noise, so you don't see that much. Or there's not even any change in the code flow. What you see here are two measurements, and they're pretty equal. So the question is, where is the information? And if you look closely, you'll see there's a little bit of difference here. And why is that? Well, as I said, the switching depends on the content of the data, of the original value and the value it's switching to. So depending on the data and the key, it will sometimes use a little bit less power, the other times a little bit more. And what you're going to do is you're going to look at those differences. So you're actually going to take the difference of those two, and that will actually be the information you're looking for. Because now you can start correlating this difference against the known values you're putting in, or the hypothesis of the key. So you could look at 5 different key values, and for each key value, try to correlate against these differences. And you'll find that only for the correct key, there is a correlation. Now I can show that a bit better. Correlation always is a bit of a difficult topic to grasp. What you see here is a correlation of input data. So this has nothing to do with the key. This is known stuff that we put in. And what we did is we just put in 1,000 random inputs into a DES. And then you correlate against your power measurement. And what you'll see is that at some points in time, there's a peak. And this means there's correlation. This means at this moment in time, that bit is being operated on, or at least there's a correlation with this bit. And actually, if you go a little bit deeper in the DES, you'll see that this is the uneven splitting of the byte, the input byte. So you'll see that this bit is operated here, but this one was earlier. So the even bit is operated on earlier than the uneven bit. And you see that this bit is a little bit later than this bit. So these bits get in order, just one after the other. And then at a later point, there's, this is kind of a distribution of the input bits over, it's an expansion. And some bits are used twice there. So you'll see 2 peaks in this case. So this is the way that correlation works. You have the U's somewhere in your signal, and if you look at each individual signal, they're noisy. But if you take 1,000 and you start correlating with your known inputs, you'll start seeing these correlation peaks, which tell you something about what's happening inside. Any questions about this?
I have a short question.
Yeah, sure. Okay, so the question is, do you do it only with the input data, or do you do it also with intermediate values somewhere? Well, in the end, you do it with intermediate values, because what you're looking for is the key. And actually, it's coming up shortly, because I'll show you how to do this on a DES implementation, and hopefully I can show you even how to break a key on a setup I've here. And in that case, you're actually going for the intermediate values. You start looking for a place where the key is used in combination with your input for the first time, preferably, because then you will have the strongest correlation. So, well, this is a little bit of an example. Actually, this is not what I'm showing here, or no, because this is talking about hardware, AES and DES in a chip, which is actually what we are seeing now in a lot of fields. What I'll be showing here is a software implementation, but you can do these attacks just as well on a hardware implementation. So there's no real difference in approach, although maybe the analysis techniques may change a little. Okay, so what I want to show here is how to break a key that's actually on this smart card. So I'm now transitioning to a power measurement setup. I'm using a box that we developed, which is doing that power measurement and tries to have a signal that's conditioned as well as possible, and also supplies the triggering. So similar to the embedded system I have here. I have to start disconnecting some stuff here. Let's see, yes, and then the trigger. Where is it? Now I lost the cable. So I'm now connecting the trigger and the signal to this box. And then I have to start moving again my cable. Hope my PC is not out of power yet. Okay. And then I move this. Oh. Just check. Yeah. No. Okay. Whoops. That doesn't look good. This works. Okay. What I'll... this is not used to a dual screen, I see. So, we have our acquisition again, and the scope is again not available. So, okay, what I'm now going to do is, first of all, I'm going to set up a measurement, and then while it's measuring, I'll try to explain what's going on, and then I hope at the end of my explanation I have results, but it's a bit of a gamble. So I have to quit this again because and now I have, okay, now it's trying to load the scope driver. I think something is not going very well. I'm losing my screens. What is happening? Okay, this key. No. Well, this is not going very well. Well, yeah, that's something that's it kind of is a crummy driver, so it needs to be ejected and injected and things like that. And then let's see, maybe now. Okay. Now it says scope ready, so that's a better. Oh, no, it doesn't see that. Yeah, I don't like this. I'm going to kill everything here and then hope it comes back on. If it's not going to work, then I'll just take an old measurement and explain it with that. But it would be kind of fun to run it. Okay. Found no power tracer. Very nice. Again. Yeah. Okay. Finally. So what I'm going to do here is I'm actually going to do a bit of processing after I've done the measurement. So what I'm setting up here is on one hand I have the scope configuration, and here I have the configuration of this device. And I have to check this for a minute. Oh, yeah, that's too good. Okay, so what I'm going to do here is while doing the measurements, I'm going to align them and resample them to a clock frequency, because I'm sampling much higher, and then aligning again. That will all be going on in the background. And while that's going on, I hope to explain why I do that. So let's see if it goes. So it's now doing the measurements. What you're seeing here is this is the first round of DES, and this is the second round of DES. And this is already the conditioned signal, so it looks a bit better. I can show what it looks like. Let's throw this one over here. And then we do a oops. Okay, so this is a bit different measurement, but it shows you the same things. So what you have here is the measurements, and if I zoom in, you'll see this is actually a clock cycle. So this is one clock cycle, and another one, and another one. So if I want to do these correlation attacks, I want to have all these clock cycles aligned. But if I look at them and I overlap them, you'll see that they're actually not aligned, because you always have a little bit of jitter in your trigger. So the first step is to align these so they actually match up. And I can do that using, well, I first want to set a example of, okay, I just want to align everything on something that looks like this. And then I say align. And in this case, let's see, yeah, sorry, now it's moving to this screen again. Now I'm moving to that screen again. So here I can set, well, how much it should be aligned, the pattern, because it's using the same pattern to find that in all the other traces. And actually I'm going to limit this to a couple of traces, maybe 10. So, and then I'll run it, and it will show you that it's including all these traces in the result. And if I look at the result, and zoom in again, and would do an overlap here, yeah, you'll see that it's kind of slow. Now they're nicely aligned. So this is what happens. Now this is on a clock cycle, but still the clock cycles could be quite out of sync with the process that's actually happening on the clock cycle. So what I showed you in the measurement is that I'm doing an align and then a resample and then an align again. And that's to make sure that also the process patterns are aligned and not only the clock cycle. The resampling is something that has to do with, okay, what is the interesting information within the clock cycle? So in this case, I'm just taking the whole clock cycle and taking an average for each clock cycle. But I could also say, well, I know that this part of the clock cycle is actually the one that contains the interesting correlating information, and the rest of the clock cycle is not so interesting. Then I can also choose to do a different kind of resampling. In this case, I'm just taking the average of every clock cycle, which results in one sample per clock cycle. So, for instance, here we have a resample, and then window here, window there. So what I do is I resample to 4 megahertz, because that is the clock I know that's used for the smart card. And then we resample, and you already see that oh, wait a minute. It looks already a bit different now, and actually the process aspect become more pronounced. And if you zoom in now, it's actually pretty clear that every sample is just one clock cycle information. And you'll see that if you start looking at the differences between them, that actually there's difference in heights of these peaks, which are actually in this case dealing with the S box of the DES operation. So let me go back to this measurement because I think it's finished. It's done 1500 traces. So that's in the time I've been talking, we've done 1500 measurements. So that gives an indication how fast it can go. And then on this S box, we're going to do an attack. But to do that explanation, I have to switch back again to my slides, because else you have no idea what I'm talking about. Then I'm also going to check the time for a little bit. Till what time did I have? 12:30? Anyone know?
12:45.
12:45. Okay, that's good. Because else I had panicked at this moment. So what are we looking at? We are looking at the DES. And what's the DES doing? Well, it's doing 16 times something like this. Where it's using the input, and then there's a static permutation. It's splitting the bits, and then it's throwing it through a function, and then combining them again, and then throwing them through a function, etc., etc. And to give you a little bit of insight in what's happening in this function, this picture is relevant because here we have another permutation, and you have to imagine that these are all static things, so these are predetermined. If you've got known input data up to this point, you'll know exactly what is here. You can just do the calculation. And this is the intermediate value you were talking about. So at this point, the round key, which is a derivative of the real desk key, is XORed or combined with the data. So at this point, it becomes unclear what the actual intermediate values are, and they depend on the key. And what happens then is kind of interesting, because here we have 48 bits, which is quite difficult to brute force, although it can be done. But then here it splits into 8 S boxes, using only 6 bits per S box. So, and after that it's combined again. So what do you see in the software implementation? We'll do this one, and then we'll do this one, and then we'll do this one, and then we'll do this one, and we combine and we go to the next step. So these are sequential executed in a software implementation. So how do you break the key then? Well, what we want to find is we want to find out what the key is. So we have some known data and some unknown data. But if we've only got 6 bits, that's 64 possible choices at this point. So that's actually something we can brute force. We can start to try to do that correlation for each of the 64 values for that key that gets combined with our random input. And that's not so hard to brute force, 64 subkeys. I have to do that 8 times then, of course, but it's a lot less than having to do all the bits at the same time. So actually the structure of the crypto is helping us here reduce the problem, because we can look inside of the box and we can look at a point where the key is split into subkeys. And that's what's actually happening. So we are going to do a correlation attack, and we are going to do it with all those keys, and then try to find which key gives the best correlation, and then we say this must be the correct subkey. And that's what you'll see in the demo now. At least I hope, because this morning I had quite a bit of problems getting actually the correct key out of this. And this is a live measurement, so it will be very interesting to see what actually comes out. What I'll do first is I'll zoom in a bit on this area. So I know that this is the area where the first S box is being done. What I didn't tell you is we only need 2 of the intermediate round keys to reconstruct the original key. So what we're going to do is we're going to do an attack on the first round and get a round key, and then an attack on the second round and get a second round key, and from those reconstruct the original key. Well, actually from this point on it's pretty point and click. Oh, now the window's here again. Try to get back again. I have to configure some things. In this case, I'm going to look at the Hamming weight, which means I'm going to look at the Hamming weight of 6 bits. And the Hamming weight is the number of ones in it, which is a measure for how many switches. If you go from 0 to the value, the ones are the ones that are switching. So if I have that happening at the same time in the CPU, because the bus is 8 bits, for instance, we can do the correlation on that combined value, and it will be stronger than if I do it on a single bit of the key. So with the first round, and then we run it, and then so here it's okay. So here below now it says this is the round key that I found, and if I scroll back up, oh that's nice, I can't see the scroll bar. Wait a minute, I'm going to resize this a bit because I can't see where I am. Okay, so if I scroll up a bit, let's say to the first S box, oh, this has gone wrong, I can already see, so that's a bit of a pity, because I can see the position where the best correlation was for this S box, and actually the best ones should be all in the same position, because I know it's calculated at that point. So actually what I'm going to do is I'm going to take a little bit less of the output and run it again to see if I get a better result there. So back up. No, I was still not at a good position. Let me check. Yeah. Redo it again. I don't know why this is so tricky, because in the past I had better results here, but now it looks even worse. This one at least looks better, so that's a good start. So what we see here is that at the same position I have different correlation values, and what we're actually looking at is the highest value. So for subkey 26 it says I found the best match, and when we scroll to subkey 26, whoops, I'm going a bit fast, whoops, here you see the correlation peak. So this peak is apparently for the first subkey the largest peak that I found, and so it goes on for all the other subkeys. So well, it looks reasonably okay, so I'm going to hope that this works. So with this information we're going to move to the second subkey, and now I think I have to take a little bit here, and then in this case I say this is round 2. I'm going to reuse this, try to find the key. Okay, well, it wasn't too good because I see a lot of mismatches. So what it's doing is now it has 2 round keys, and it's going to reconstruct the original key. But there's overlap, there's redundancy, and that you can use as a check to make sure that you actually had 2 correct round keys. And actually in this case there's quite a few mismatches. So one round key is saying this bit should be 1, and the other round key is saying this bit should be 0, which is a conflict. So there's a wrong choice for the subkey. Well, I have to say this is a pretty bad result. What should be here is Cafe Babe and Dead Beef. Well, I don't see it. So I'm trying to think I've got the measurement that does it correctly, but I don't. So I'll keep on going. If you want to see a better example, I will maybe later today. So I'm going to move on to what you can do about it, because that's actually well, just as important and just as interesting. Well, this looks nice. Now, this is a nicer correlation peak. This is what we want to see, like huge peak and nothing in the other ones. What can you do about it? Well, the first thing is you want to decrease the leakage. You want to just prevent that so much information is coming out of that channel. Now, as I showed, it's about switching if you look at power. So what can you do against it is something that counteracts the switch or balances it. So if you have one switch going up, at the same time you've got a switch the other way, there will always be equal power consumption, whatever kind of combination of data you're using. So in smart card technology, this is called dual rail technology, where you actually physically double all the buses and drivers, etc., to try and create as much of a balanced power consumption through a full crypto operation. Another one is to just limit the number of operations per key. Because if you see that I have done 1500 measurements and I'm not getting the key, that might be to noise, it might be to other countermeasures. If I only get a limited amount of number of operations on the key, then I cannot break it. A well-known example is that trying to break the GSM key, there was kind of this Oracle attack. In the GSM chips, they try to limit the number of requests you could do for the key before blocking your GSM SIM. Because they don't expect the phone to ever do so many requests, and within a lifetime, that would be a way to reduce the chance of an attack. The other one is increasing noise. Increasing noise can be done by making it very difficult to align, for instance, but also make the noise level, so the signal level, very low. So you need to make a lot of measurements to get that signal out of the noise. And you can do that, of course, in software, partially. but also in hardware. So what does it look like? If you have passive attacks, so we're now just looking at the system, we cannot influence it, then there are two places that you actually want to make it more difficult or prevent the leaking. One is hiding, which what you're actually trying to do is the same thing as the balancing. You're trying to break the relationship between the power consumption and the actual process value. But you can also do this algorithmically. So you can change your algorithm, introducing a random maybe in there in a masking way to try and break the relationship between the power consumption that the subsequent processing steps will take and the actual value in the algorithm that you are processing. And actually, maybe I'm not doing it correctly, because that's actually more the blinding step. So the algorithmic step is what we call blinding. Anyone familiar with blinding? Heard of RSA blinding? I'll show you later, but the idea is that you pre-process values with randoms and then go through the whole algorithm and then unmask or remove the blinding again at the end. And then the whole middle chunk where all the real crypto happens and your measurements is effective will not show you the real values, but the ones that are masked with random data. So if you look at an algorithm, then you have the algorithmic value, then you can change your algorithm by using the masking and blinding techniques, and you get the real process value, the value that is loaded by the load instruction stored in the memory. And then you have the hiding, trying to obfuscate, as it were, the actual power consumption by using the balancing techniques, etc. Well, this is an example of changing the crypto protocol. If you, and actually this is an example of Paul Kocher, the one that kind of was the first publisher of the DPA attacks, and has quite a few patents also in this area. But some of the things that they published about doing your protocol in a different way, preventing you to have a single key. So in this case, if you're doing transactions with another party, and you start with the same shared key, but then for every step you start keeping a transaction counter and hashing your key to a new value, preventing side channel attacks on the key, on the real key, because there's no one key. Every transaction there will be a new key. Oops. So one of the things with the correlation attack is that you want to have alignment. You want to have the same value being processed at the same moment in time, because that's only when your correlation attack will work. So trying to make it more difficult to have that same operation happen at the same time every time you do a measurement is a countermeasure. But there's also the simple thing like just removing any time dependencies. So if you have an SPA attack, which is possible on a lot of the embedded systems today, even single instructions can be visible. So you want to prevent those also of having an influence in your system. So if you have a choice on a bit value going left or right, you want to have exactly the same execution path based on that. Okay, then we can do all kinds of noise generations, and I'll go over this a little bit quicker. One thing is to insert random instructions, so the position that the actual processing of the value happens starts shifting around. Of course, it's necessary to not being able to recognize those instructions. So if it's only nop, 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 and you can somehow recognize that, then it's also quite trivial to take them out of your measurement and align the real processing moments again. So this is an example. So if you have some instructions, then you can start inserting at random positions NOP instructions, and if I measure at this time, then now the first is equal. But now I'm correlating an XOR against a NOP. and here an op against an XOR, and here an add against an add again. But here the inc and the compare are also out of sync. And you can imagine if you do this a lot of times, and especially if your trigger is here, but the interesting operation is here, that this random instruction starts to have quite a significant influence. And that's also the reason why a triggering moment is important, because if you don't have any pattern, because there's a lot of noise, then it becomes very tricky to see. Which maybe you can see this difference when you take a lot of averages, but then that doesn't allow you to do a DPA attack. So these are quite common countermeasures that we see in chips. And these random instructions can even be random wait states. So in hardware, chips introduce wait states between the core and the memory, for instance. Okay, shuffling is another one. You can just say, why execute in order? Why always first S-box, and why not randomize that? What does it do for the leakage? Of course, it still leaks, but you will have to do many more measurements. Think about 8 times more to actually get the same number of S-box ones, and then you can consider the rest turns into noise. So you just need to collect the same number of S-box ones again in the first row, which will happen, of course, if it's truly random. You don't have that much choice. If you want to move to a better implementation, that's not, how should I say, a little bit of ad hoc and already proven to also leak, because it just takes more time, then you really need to move towards things like masked implementations. And this is also what we see now in modern smart cards, that AES and DES engines are using masked implementations to already also make it more difficult to find that correlation point. Although they are still there. Even masked implementations can be broken using side channel. Only the level of expertise and the advancedness of it goes up quite significantly. What you'll see is also that everyone is stacking all these countermeasures. So no one is doing only one thing and depending on it. It's very much a thing of combining a lot of these things. We have seen things like also introducing full false cryptos in between the real crypto, just to confuse an attacker and make the correlation attack much more difficult. Okay, so I had more demos, but I just don't have the time for that. But I thought I'd also show something with public key crypto. So what I'm going to do is I have an implementation on the embedded system of an RSA. And the first implementation is actually a pretty straightforward implementation. Actually, I'm not completely sure if I had a RSA. Oh, this is actually also good for explaining. Then we can show it later here. So if you have got an RSA implementation, what you're doing is basically two things. To calculate the exponent, you're doing something that's called a square and a multiply. And that's got to do with the way you do an exponentiation. It's called the bitwise binary exponentiation. And for a 1, you do a square and a multiply, and for a 0, you just do a square. Now what happens is that these are distinguishable. For some mathematical reason, a square is not really identical as at a multiply, which you can a little bit imagine because you're actually multiplying exactly the same zeros and ones, and in a square, in a multiply, that's random. So, and once you can see a variation between a square and a multiply in a signal, it's just looking at the key bits. So what you're seeing here is if there's a distance here is a bit shorter and this distance is longer, and this is a square and this is a multiply, then I am seeing a 1 bit and a 0 bit and a 1 bit and a 0 bit and a 1 bit. And I can just visually see the key bits of the exponent, which is the secret key for an RSA operation. Now, let me just, completely lost my track. I have to move to another screen for a moment. So, and then I have to move the cable again. This is really terrible for the demo. This is okay. So, where's my screen? Oh, it disappeared. Wait a minute. Okay, there we are again. Let's see. Okay. Trigger. So now I can make a measurement again. I hope. Scope not available. This is so. Since we have bigger scopes, we don't work too much with these anymore. But okay. Okay, if this is not going to work this time, I'm going to switch back to the talk. Okay. Scope ready. Wow. Okay, so what do we see? If we do a measurement. Okay. Well, at least we see an RSA. So in this case, if we zoom in a little bit, what we'll see, and now this is not so nicely as the previous one, but if you look closely, you should be able to see that there's kind of a pattern where we have a few of these small ones and then a bigger one, and then here again. But this one is slightly larger than this one. And that's actually the difference in this case between the square and the multiply. So again, so this is a square, multiply is a 1. I think this is a square, and here it's bigger again, so it's a 0, 1, etc., etc., etc. So the next step, in this is the following. Okay, so this is the background still on the square multiply. So you see that if for every bit you do a square, and then only for the 1 bit you do a multiply. Now another implementation that you can do is you can do an RSA not for a 1 bit, but for 2 bits at the same time. You have to do a little bit of pre-computation. But then what it turns into is that you do a number of multiplies and then squares, sorry, and then a multiply with a pre-computed multiplier. But if you look at the order, there's no dependency anymore on the key bit. So the multiplier is now dependent on the key bit, but the multiplies and the squares are equal for each 2 bits. So it's a simple way to do this, and it makes it at least resistant to the SPA attack. But this does not make it resistant to a DPA attack, because the constant that's used in the multiplier is still different for the key bits, and you can find that during using a DPA attack. Right, so an even better way to do it is again to use the blinding technique. I'm not going to explain the whole crypto, but this is the normal crypto, and now you can use a random, and you can do that with a pre-computation, and then at the end remove it again. And what happens is that with pre-computations, if you leave them out, the actual calculation is now not anymore using the crypto exponent. It's using a randomized version of it, making it much more difficult. So you're using CR now here. So making it much more difficult to find the D value. And because it's algorithmic, you don't really depend anymore on your hardware also. I think I need to start finishing off, so I'll just show you the RSA at the end. What I wanted to say about this is what you see using these attacks is that actually pretty difficult to determine if your system is leaking. You really need to measure and test to discover what kind of leakage your system has. And it's quite difficult to predict this. It's in this sense, it's a very fuzzy field. There's no, a theory of countermeasures and then you use them and you're done. So verification is pretty important. And actually, it's also moving into the FIPS, although there's still discussion about how far it will move into FIPS evaluations. But the expectation is that there will be a section on it. One thing also about this field is it's a bit a strange field compared to a lot of others in that patenting is quite significant in this area. Paul Kocher, who was the first publisher, works for CRI in San Francisco. They patented quite a few of the countermeasures and the attacks in this field. But there are also others that have patents in this field. And when you implement a countermeasure, you have to check if this falls under any of those patents. And the best thing is to get in touch with them over this. The thing about it is also that I've shown you all kinds of simple ways like noise induction and things like that. But to do it really well requires a significant effort. Creating a masked implementation of an AES is not a trivial thing. And they actually also have quite a bit of knowledge in this area. So the conclusions, I think that the embedded systems will surely see in the near future a lot more of these side channel attacks, although timing is probably one of the more prominent for the moment. But also the power and EM attacks are very successful. So developers and implementers need to start thinking about these implications and also start to look at their development techniques to see in how far they need to implement better library routines, for instance, for comparisons, DES implementations or RSA implementation that implement blinding, etc., etc. So, and you can see that actually doing this does make it more difficult. So it may not prevent it, but it may be the difference to, a very simple attack that someone at home can do to an attack that an advanced attacker needs to go through a couple of weeks of analysis for. So, and that's actually the level that you want to get it to, often in these cases. So one short demo left. Oh, now my PC went off again. Oh, it's demo hell. Well, actually, I think, well, if anyone wants to see it, you can come up, because now I'm not sure if we still have left time for questions, then it makes more sense to finish it off now. Yeah, so that concludes my presentation. Any questions?
Are these techniques really hard to do in an environment where you have a modern processor like PAM that's got deep pipelines and hyperthreading? Does that sort of extra noise complicate the analysis?
Yes, definitely. It does complicate it. But if you look at the implementation, it really depends how they're doing it. And if you have a software implementation, especially one that's using the external DRAM now and then for critical data, you'll see huge signal in a chip. So we've seen RSA implementations in modern CPUs that leak quite significantly. So it depends. It does make it more difficult. Compared to a smart card, it's a different world, but there is no countermeasures. So it does leak. The question is more how to get it out of the noise that peripherals are creating. No, Chris.
And modern communication devices, does the range of countermeasures sufficient if this conduct will be practical, or this attack is still practical devices?
On which devices?
On a modern communication device.
Like a mobile phone or?
Like 3G phone.
I think on mobile phones and CPUs like that, it's very relevant. If you would store a secret in there, then you can do a successful attack. Do note that an important step is that you can control the crypto operation as accurately as possible. So running your own code on the system is often, well, it's not a precondition, but it's very nice to have. Or you have to have a way to drive the crypto with your own input or get the output in a consistent way somehow. To trigger, etc., etc. So those complications are actually the ones that you don't see in a smart card, because in the smart card you send it I/O, it happens, you trigger and you measure, it's clearly defined. In an embedded system, this is often more the obstacle to get the crypto with the key actually happen at a certain moment in time with known data that you can extract. Jan?
You just answered part of my question.
Okay.
A lot of what you established here depends on hammering. You're persuading the same operation to happen over and over so you can time it, so you know where your triggers are and
right.
Okay. So if you're talking about something that has platform integrity checking, where you can't very well inject your own code into it, how much more difficult does that make it?
It depends kind of on the system. For instance, if you have a set-top box running a recorded PVR movie, you kind of have the system where you have the known input and it happens inside. So the question is, how well can you isolate it? But you can feed it in again and again and again. So you can run the system with its own software and still have the crypto doing something known with random input. So yeah, it depends then on the combination of the rest of the system if this situation can be created. Of course, it's very different from you still have to think about that. It's not like, oh, I think it's difficult, so it must be difficult. An attacker will find ways to do this, maybe in unforeseen ways also. So it's difficult to predict, but definitely something that makes things hard. Yeah.
What type of spatial resolution does your EM sense at?
You mean bandwidth?
Like how many square millimeters?
Oh, okay. It's about 1 square millimeter.
And that's through the package, right?
Sorry?
That's out from outside the package?
Yes. So at the bottom here, there's like this small stick, which has a coil on the tip of it.
What's the future hold?
Well, I think for systems like in the pay TV area, it becomes very relevant because you see a lot of the chips getting all this hardware now on board of the chip. So for people to try and break them, they will need to get into that chip somehow. If that will be more physical attacks or these kinds of attacks remains to be seen. But we've seen that they can be quite successful, like they have been on smart cards in the past also very much. Okay.
Thank you.
Oh, no question.